Okay, welcome back. We are going through the Rust programming language book, and we are on to defining and instantiating structs. So, structs are similar to tuples discussed in the tuple type section in that both hold multiple related values, and like tuples, the pieces of a struct can be of different Rust types. So, unlike with tuples, in a struct, you'll name each piece of data so that it's clear what the values mean. And that can also be useful, I think, for searching code, which is not directly about the typing of the code per se, but if you're pulling up tools to help you navigate code, I find that the names can be helpful. So adding these names means that the structs are more flexible than tuples. You don't have to rely on the order of the data to specify or access the values of an instance. So that's also true if you're thinking about like refactoring a data structure. Even just refactor, not rewriting it to do something different or substantively, even if it's just a refactor that it's like a substantial amount, you can save yourself a lot of work by using a struct when considering ordering. Because with a tuple, if you write the code under a specific ordering and then you have to insert more positions in between for some reason, that can be a bit of a pain. So to define a struct, we enter the keyword struct and name the entire struct. A struct's name should describe the significance of the pieces of data being grouped together. Makes sense? I mean, there's going to be what is sometimes broadly called an organizational principle, some reason for why we're putting them together. And if you can put that into a name, that can help people recognize what the struct is for, even before they read the implementation of the struct. Then, inside curly brackets, we define the names and the types of the pieces of data, which we call fields. Not to be confused with other notions of field. It's not a soccer field, and it's not necessarily a field in a physics sense. For example, listing 5-1 shows I say physics or math. Anyway, not to get into that, shows a struct that stores information about a user account. All right, so let's create an example where let's go cargo init, and we'll call this one user. Get in there, take a look at that code. It's going to be hello world by default, and actually even outside of the main function, we can just leave that for now. Let's go struct and put in user. So that's our struct keyword, and that's a user, which is not a keyword, it's just something we chose. And inside of that, we'll go and define active as a field. Notice that we're putting commas in the definition to separate. Username, string. Username is going to be of type string. Email can also be of type string. Sign in count U64. Now, some people might actually break these things down themselves into other types of data. Sometimes enums, for example, or that you might have some abstract rules about what counts as an email, because not any string counts as an email. Okay, so to use a struct after we've defined it, we create an instance of that struct by specifying concrete values for each of the fields. So these are really just placeholders for things to exist, and these are the names that you can access the fields by later, but for whatever the content is, you have to supply that when you make the struct. So we create an instance by stating the name of the struct and then add curly brackets containing key, value pairs, where the keys are the names of the fields and the values are the data that we want to store in those fields. We don't have to specify the fields in the same order in which we declared them in the struct. In other words, the struct definition is like a general template for the type, and instances fill in that template with particular data to create values of the type. For example, we can declare a particular user as shown in listing 5-2. So let's take our main function and put something in here. Let user1 be bound to the value of user. Put a semicolon at the end there. So we'll say active. What about active? Active has to be of type bool, so we'll put an example boolean, in this case true. We can put in not user, but username, and that has to be a string. So we'll call this from and we'll pass in a string literal, in this case just some username, 123. Okay, and we can pass in an email of type string from, and we'll initialize a string using that method, someone at example.com. And then sign in count, how many times the user has signed in or something like that. Set that to 1. Okay, to get a specific value, we use dot notation, because you think about it, it's like, okay, we defined this data structure that will exist in memory. Hopefully there's no bugs. Let's just try to build quickly. Okay, so there's some warnings because I didn't use any of these fields, and Rust's compiler's very on top of that of I didn't use the user1 and I didn't use any of its fields. So that's okay though. Okay, so the next piece is, we want to be able to access that data and potentially do something with it. So to get a specific value from a struct, we use dot notation. So similar to dot notation as you would find it with objects in other programming languages. For example, to access this user's email address, we use user1.email. If the instance is mutable, we can change a value by using the dot notation and assigning into a particular field. Listing 5-3 shows how to change the value in the email field of a mutable user instance. So we can set the entire user to be a mutable variable. Actually, off the top of my head, don't know if you can assign just subcomponents. I suppose that would be part of the type, maybe? Like mute string? I don't know. We'll have to go back and find out at some point. But anyway, user.email, and we could reassign that to be bound to some other value, like another email dot at example.com. So that's an example of changing the value in the email field of a user instance, and we had to set this as mutable to make any of these fields inside or mutable as well. So note that the entire instance must be mutable. Okay, there's our answer. Rust doesn't allow us to mark only certain fields as mutable. There's our definitive answer to what I was trying to remember there. As with any expression, we can construct a new instance of the struct as the last expression in the function body to implicitly return that new instance. So listing 5-4 shows a build user function that returns a user instance with the given email and username. The active field gets the value true, and the sign-in count gets a value of 1. All right, so let's put together that function. In a sense, I'd almost say that this is more of like a factory pattern than a build pattern, but maybe the word build here is not meant to be like a build pattern exactly. It's just called build. And what should we put in for values here? We'll return user. Just remember with Rust, we don't need to say return like this. It's just going to tacitly know that the thing to return is user here. We'll say active is true. Username is whatever the username is that's passed into this scope here. Email is likewise going to be the email. And the sign-in count is by default 1, which might make sense for some problems. Okay, there's our build user function. Now it makes sense to name the function parameters with the same name as the struct fields, but having to repeat the email and username field names and variables is a bit tedious. If the struct had more fields, repeating each name would be even more annoying. Luckily, there's a convenient shorthand. So this is just an attempt to save some boilerplate. What are we going to do inside of our build user? We'll find out. So because the parameter names and the struct names are exactly the same as in listing 5-4, we can use the field init shorthand syntax to rewrite build user function so that it behaves exactly the same, but doesn't have the repetition of username and email as shown in listing 5-5. So what are we doing here? I mean, we've still got the email and username passed in as strings. We're still going to return type user. It's of course the user struct. We pass in active, and here we can see that we just pass in username, and it'll automatically match this parameter field with with whatever happens to be the same variable in the function scope here. So that's very nice. As a shorthand, you just need to remember that that's what it's doing. So we don't have to type out username and email for this builder pattern, or sorry, this build user function. Okay, so the listing 5-5 description says a build user function that uses field init shorthand because the username and email parameters have the same name as the struct fields. Totally. Here, we're creating a new instance of the user struct which has a field named email. We want to set the email field's value to the value in the email parameter of the build user function. Because the email field and the email parameter have the same name, we only need to write email rather than email:\email. Yeah, that's nice. So, on to another little subtopic here, creating instances with struct update syntax. It's often useful to create a new instance of a struct that includes most of the values from another instance of the same type, but changes some of them. So in some sense, it's like using an existing one as a template for making another. But you can change some of the values just selectively. Okay, so you can use this. You can do this using struct update syntax. I feel like this is actually a very handy way of, what could I potentially use this for? I feel like if you had like a default, like a function that built a default version of it, and then you just wanted to update certain fields. I'd have to think about when to use this. I'm not sure I would use it in that case. I think I'd still want to explicitly just make one of them. I feel like the advantage there is really that you've already got one, and you want to make another that is similar. So like, depending on how you're representing a thing and the state of that thing, and you have to like make another copy for some reason and then modify it, something like that. I'm not sure. Okay. Suffice to say, we'll have to think about how to really make the best use of that. But the point of this is to make it easy to make another one that's slightly different, supposing you've already got one. So first, in listing 5-6, we show how to create a new instance in user 2 in the regular way, without the update syntax. We set a new value for email, but otherwise use the same values from user 1 that we created in listing 5-2. Okay, so what are we doing here? That was our mutability example. I don't think that has to be mutable. And what are we doing? We're going to say let user2 be bound to the value of user. And we're going to say that the active field has user.one active, whatever that may happen to be. Username, we could pass in user.username. Email could be bound to some new string, another at example.com. And our sign in count could be user1 sign in count. Close this off with a semicolon. So creating a new user instance using all but one of the values from user 1. The special syntax is not being used here. We'll get to that, but this is what you might imagine doing, is going, I kind of just wanted user 1's active status, their username, and their sign-in count, but not their email for whatever reason. Using struct update syntax, we can achieve the same effect with less code as shown in listing 5-7. The syntax ... not to be confused with like the range syntax, specifies that the remaining fields are not explicitly set, but they should have the same values as the fields in the given instance. So let's cut away everything but the email here. And what are we going to do? We are going to say .user1, which basically means use all the same values for all the fields of user1, except for the ones that we've already overridden here with email in this case. So listing 5-7 using struct update syntax to set a new email value for a user instance, but to use the rest of the values from user1. Okay, great. The code in 5-7 also creates an instance in user2 that has a different value for email, but has the same values for username, active, and sign-in count fields from user1. The .user1 must come last to specify any remaining fields should get their values from the corresponding fields in user1, but we can choose to specify the values for as many fields as we want in any order, regardless of the order of the fields in the struct's definition. Now, note that the struct update syntax uses an equal sign like an assignment. Does it? Well, yes, we use it to bind to a new variable. That's true, if that's all that means. Because it moves the data, just as we saw in the variable and data interacting with the move section. In this example, we can no longer use user1 after creating user2 because the string in username field of user1 was moved into user2. If we had given user2 new string values for both email and username, and thus only used the active and sign-in values for user1 values from user1, then user1 would still be valid after creating user2. Both active and sign-in count are types that implement the copy trait. So the behavior we discussed in the stack-only data copy section would apply. We can also still use user1.email in this example because its value was not moved to user1. Okay, a little bit long-winded there, but basically you do have to watch out for this problem of that you may be unable to use user1 or whatever the previous existing struct is, depending on how you've assigned things. Okay, so let's creating different types with tuple structs. Let's take a look. Rust also supports structs that look similar to tuples called, well, tuple structs. Tuple structs have the added meaning that the struct name provides, but don't have names associated with their fields. Rather, they just have the types of the fields. Tuple structs are useful when you want to give the whole tuple a name and make the tuple a different type from other tuples, and when naming each field as in a regular struct would be verbose or redundant. So to define a tuple struct, start with the struct keyword and the struct name followed by the types in the tuple. For example, here we define and use two tuple structs named color and point. Let's do it. So let's hop up to line 10 here. And we'll just delete all of that and start afresh. So the first tuple struct we're going to define is called color, and it takes an i32, that's a signed 32-bit integer, and it actually takes 3 of them, specifying what I assume is like a color, the set of color fields of red, green, blue, or something like that. And then we're also going to define another one called point. Hopefully the point of this example becomes clear soon enough. And we pass in for color, maybe 0, 0, 0. I think that's for like something like a 0 to 255 kind of sets of color values for each channel. Point 0, 0, 0. Sure. Note that black and origin values are different types because they're instances of different tuple structs. Right. Black is going to be of one type. Oh, I don't have LSP set up right now. And origin, these will be of different types for sure. One will be a custom type for color, and one will be of the custom type of point. So Rust is very type heavy, and this is a way of basically expanding the set of types that are supported in Rust, but from a programmer user point of view, not from a language development point of view. So each struct you define is its own type. Even though the fields within the struct might have the same types, That is, it's not just the types alone, and I think this is the point of their example, is that we've got a triple of I32s and we've got a triple of I32s, and yet the point type is a different type than the color type. For example, a function that takes a parameter of type color cannot take a point as an argument. Cannot take an instance of point as an argument, even though both types are made up of 3 I32 values. Otherwise, tuple struct instances are similar to tuples in that you can destructure them into their individual pieces, and you can use a dot followed by the index to access an individual value. Unlike tuples, tuple structs require you to name the type of the struct when you destructure them. For example, when you write let point xyz is bound to the value of origin, to destructure the values in the origin point into variables named x, y, and z. So like this, if I wanted to say let point x, y, z be bound to the value of origin, that should be valid. Lots of complaining about these fields not being used, but otherwise that appears to be correct. There we go. Now, moving on from tuple structs. Let's clear that out, although I think that they're potentially useful. Not a lot to say on them at this point. It'll be much more interesting in some sense to start building things, more complicated things, because then you can start to see why these different data structures are more or less useful depending on what you're trying to build. And especially for things like simulations, it's kind of a choice of, when you're doing the development of the code, how rich you want the representation to be. Like, how detailed are things supposed to be? You might, in some cases, represent something merely as a number. In some cases, something might be an ordering, or in other cases, it'll be a more complicated kind of structure altogether. Okay, so let's move on to another topic here of defining unit-like structs. You can also define structs that don't have any fields. I'm not yet sure why we want to do this, but this is a thing in Rust. These are called unit-like structs because they behave similarly to the unit type. The unit type that we mentioned in the tuple type section. Unit-like structs can be used when you need to implement a trait on some type, but don't have any data that you want to store in the type itself. Right. I mean, I guess it's a very lightweight way to define a type, although I would still need to do some more reading and learning to make sure that's really what you should go to as a way of defining new types, but certainly this is on offer. I wonder also if you can similarly do that with enums or not. Not that we've gotten too far into enums, but that's a question on the top of my mind. Okay, so unit-like structs can be useful. We'll discuss traits in Chapter 10. Here's an example of declaring and instantiating a unit struct named always equal. So, like any kind of normal struct, we would use the struct keyword, and we just type out always equal, semicolon, and then we might say something like define a variable, let subject be bound to the value of always equal. Great, and that's it. Easy. So to define always equal, we use the struct keyword, the name we want, and then a semicolon. Yes, I mean, it's a statement to make these kinds of definitions, so remember your semicolons. No need for curly brackets or parentheses, which is nice. I guess that saves you a little bit of boilerplate because the meaning is otherwise understood. Then we can get an instance of always equal in the subject variable in a similar way, but we're not using the struct keyword here. That would be an error. Imagine that later we'll implement behavior for this type such that every instance of always equal is always equal to every other instance of any other type. Perhaps to have a known result for testing purposes. I guess so, yeah. I mean, some special types, always true, always false kind of things. I am curious. Okay, let's just make sure this compiles. Build cargo. Spelling typo. I really should turn on some quality assurance here, but Kafka build. And I am just curious what the error is, because I think we should get an error there. You can't like assign a declaration to a variable like that, I don't think. Yeah, expected expression. Okay, great. We wouldn't need any data to implement that behavior. You'll see in Chapter 10 how to define traits and implement them on any type, including unit-like structs. Good to know. Okay, I'm quite curious about this one. Ownership of struct data, because we eventually in Rust have to care about what things own what other things. So in the user struct definition in listing 5-1, we used the owned string type rather than the reference to stir string slice type. This is a deliberate choice because we want each instance of this struct to own all of its data, and for that data to be valid for as long as the entire struct is valid. It is also possible for structs to store references to data owned by something else, but to do so requires the use of lifetimes, a Rust feature that we'll discuss in Chapter 10. There's a lot of things having to be deferred here to like fully understand it, but you have to have enough put in front of you that you can work with these things. So lifetimes ensure that the data referenced by a struct is valid for as long as the struct is. Makes sense, I suppose. Let's say that you try to store a reference in a struct without specifying lifetimes, like the following: source main.rs won't work. Okay, let's give a try. Let's take a look at their example. So we'll define struct with the struct keyword, and we will say that there's a user type, and we'll declare that it has a field bool, a field username, which takes in a reference to stir, email that also takes a reference to stir, and a sign in count, which will take a U64 type. And let's define a user. Let user1 be bound to the value of user. And we'll initialize this one, instantiate it with true username, some username, 123, email, someone at example.com. Assuming I don't have any other typos. Okay, we get an error. Look at that. So error E0106, missing lifetime specifier. So we have in our username field a reference to stir, and it expected a named lifetime parameter. So there's a help. Consider introducing a named lifetime parameter. Here it would be a type brackets and quote A. And then we have that active would be bool, and username would have this reference to the lifetime stir. And then we have a similar thing again with email of a missing lifetime specifier. It says the same of user should have a lifetime, and then the field itself should have lifetime. So that's important to keep in mind. I feel like that would be a foot gun for a lot of people, including myself, to go like, I just read about struct, let's just make one. And we just learned about slices. So why not? Well, it's because Rust needs to completely lack ambiguity about how long something should exist and who owns it. Okay, so that's actually the end. In Chapter 10, we'll discuss how to fix these errors. Dang, I mean, if you're really wanting to get started like right now with some complicated lifetime stuff, you're just gonna have to wait. So, to fix these errors so that you can store references in structs, but for now we'll fix errors like these using owned types like string instead of references like reference to string. Yeah, I actually really like passing references though, so if you're like me, you're just gonna have to wait to do the cool stuff. Anyway, that is the end of this video, and hopefully that gave you some useful and interesting information about defining and instantiating structs. It's very straightforward to make them, but clearly there's a little bit more than meets the eye when it comes to dealing with lifetimes. Hope to learn more about that soon. But in the meantime, enjoy the rest of your day.